Right. Hi, everyone. So I'm going to be talking about some work I've been doing with help from uh, many different people from UC Berkeley, University of Nevada, Park Service, but I've listed some of the key recent collaborators here. Was it?
Sorry, just grabbing my things.
Yes. So I called this talk Soil Moisture in the Wildfire Continuum because in a lot of the places where I work, fires are fairly frequent. It can happen every 10 years or even more often. So really the post-fire is the pre-fire for the next fire rather than having this false dichotomy of just before fire and after fire. No?
We've got
Ah.
too fancy for good here. Oop. Okay, try now.
There we go. Thank you. So there's a lot of very important feedbacks between vegetation, fire, and soil, and these are all mediated by soil moisture. And predicting exactly what's going to happen to the soil moisture in the hours, days, weeks, months after a fire can be really complicated because there are a lot of counteracting effects. You remove trees, there's less water being pulled out of the ground by roots. There's also less interception of the rain coming in, both of which will increase your soil moisture, but your ground's more exposed to the sun and the wind, so you have more soil evaporation. Removing trees and blackening surfaces can do a lot of different things to the snowpack, either increasing or decreasing soil moisture. And then, of course, if you have the high severity fire that makes the soil hydrophobic, and increases erosion of your top layers of soil, that's going to decrease the amount of water that infiltrates and that can be stored. So this is an overly complicated diagram that I put together years ago. It's just a conceptual model, just trying to illustrate all of the many feedbacks that you need to take into account when trying to think about what's happening in this fire continuum cycle. And for example, there's feedback to the type of soils that you have, and the amount of soil moisture is going to determine what kind of vegetation can grow in a location, and how much vegetation there is going to determine how much transpiration, interception, et cetera, which in turn affects the soil moisture. And then both the soil moisture and the vegetation cover are going to affect your fuel moisture, which then affects how large your fire is. And that fire is going to impact the soil moisture, which then impacts the conditions that are going to be present the next time there's an ignition. And a really great place to study these kinds of complex interactions over multiple fire cycles is the Illilouette Creek Basin in Yosemite National Park. So like most of the Western US, Yosemite was fire suppressed for a long time. It naturally had a fire return interval at a lot of the elevations around 10 years, but then wanted to protect infrastructure and forests, put the fires out, then realized that the baby sequoias couldn't grow anymore and there were other ecological problems. And so the Park Service wanted to try allowing fire back on the landscape. And Illilouette Creek Basin is one of the first places where they tried that in the early 70s. They decided that under most circumstances, if there's a lightning ignited fire, they would allow it to burn. And there have now been dozens and dozens of fires over the last 50 years. And as part of my PhD, I set up these 3 weather stations back in 2015 on a hillside that had been completely forested at the end of the fire suppressed period, but then had burned twice since the 70s by the time I got there. And part of it was still a forest labeled in green there. Some of it had converted to shrubland and some had opened up into a nice wetland. And the top here is what it looked like when we installed everything in 2015. And then serendipitously, there was a fire that came through in 2017. I promised I did not start it, but it burned through the stations. The Park Service was very helpful in helping us evacuate all of the electronics from out of the fire's way. We left the soil moisture sensors buried, and that soil protected them, and they were fine after, just dug the wires back up, plugged them back in, and everything worked great. And one of the biggest changes we've seen from the fire is that's most clear and obvious is in terms of the snowpack, actually. And a lot of the literature out there and observations are that you get faster snowmelt and shallower snow after a fire. And that does happen in a lot of places. But it's also very location dependent. In places with relatively warm winters, the way the energy balance works out is that actually more open areas retain snow longer. Even though that seems counterintuitive because the sun is hitting them more, you don't have tree wells forming in the open areas, long wave radiation coming off the trees. I think it also makes a big difference if you've had multiple fires. You can see over here on the left, there's tall burned snags that's creating a lot of black carbon that can fall onto the snow, darken the surface, and make it melt faster, versus that burned shrub area where we have the nice deep snow. The snags have been burned down because that's the third fire in the previous 40 years or something like that. And so there's not a lot of sources of black carbon. The snow's nice and white. It's sticking around. But then in the live forest, those trees themselves are actually melting that snow away. Here's another picture of that snow disappearing earlier in the forest. And if you look at the difference in timing of the first snow disappearance date in the spring, consistently every year we were able to get good data. The shrub area and the wetland area kept the snow like at least 5 days and up to over 50 days longer than the nearby forested area on the same hill slope. And the day of the year, DLY, that the snow completely melts away is positively correlated with what the water content is in the soil in July. And this is not North Carolina where you get lots of rain in the summertime like yesterday. In this area, basically most of your precipitation for the year is going to fall in the winter as snow. And then that slow snow melt at the start of the growing season is what's providing most of the moisture that's going to be available to the vegetation throughout the summer. And so that's why this summer water availability for plants is really driven by that snow. So if you're melting the snow off earlier, then that's reducing what your plants are going to have available to grow. And this is a time series over 10 years of soil moisture data that we have from those 3 stations I showed earlier. And the wetland site stayed almost saturated at 1 meter deep. And partly that's because of the really deep snowpack that we had of the wetland. It's mostly because of some subsurface processes. There's a fracture zone that we found that's providing deep groundwater to keep it wet. But you can see the shrub site in the brown is getting wetter during the winter and during that spring snowmelt, and it's staying wetter into the summer compared to the forested site, which partly is because the forests have more roots that are sucking up water, but also because of that earlier snowmelt. And just a quick note, something we also saw that was really obvious was right after the fire that happened in 2017, indicated by the little flame, the soil temperature rose a lot, even 1 meter deep, because it was more exposed to the sun. And now as the shrubs have grown back on that brown line, we're back to the pre-fire soil temperature conditions. And I'm going to show a few plots from a random forest machine learning model that I created using some of the data from Illilouette and also other parts of Yosemite. And don't worry too much about how these graphs were created, but basically the way to interpret them, for example, on the left, as NDVI increases, which means you have more vegetation that's actively transpiring, not given any other information about the site, you can expect the soil moisture to be higher. So it makes sense. Where the soil is really wet, you're going to have lots of vegetation. And then topography is also important in the soil moisture. Where you have really low slopes, water can gather, it's likely to be wetter. But then also you can look at times burned. The water content that you expect given the number of times burned, again, sort of averaged over all other possible conditions that you might have. It's slightly wetter in places that have never burned, because those really wet places can act as a fire break. But then also once you get to 4 or 5 times burned, you also have slightly wetter soils. And I think that's partly because once you've burned that many times, you're getting these really low severity fires that are reducing the transpiration, but they're not affecting the soils too much. And when you've just burned 1 or 2 times, you're more likely to have these high severity fires that are going to cause those hydrophobic conditions that are what people often think about when they think about fire affected landscape. These are some measurements we took after a high severity fire. And on the right, you can see that the hydrophobicity as measured by water drop time increased in the sites that had burned as opposed to the controls we measured before the fire and after the fire, year before, year after. And the places where hydrophobicity increased because of the fire, you also see lower soil moisture in the post-fire conditions compared to pre-fire. But hydrophobicity isn't just caused by fire, as someone mentioned over here before. It's often assumed that you're automatically going to have higher hydrophobicity after a fire, but actually places that are long unburned can also have really high hydrophobicity naturally, just from the organic matter that's in the soil. And in Yosemite, we found that actually canopy height and other vegetation indices were a much better predictor of whether the soil would be hydrophobic compared to if it had burned. You do see slightly more hydrophobicity in the first year right after a fire on average, but then also once you get to multiple decades without a fire, the soils get equally hydrophobic. And we also saw this in a very different landscape in the sagebrush ecosystem that I've been working in outside of Reno, where we burned some study plots last fall. And you can see that in the intershrub, the relatively bare ground or maybe some grass, we have very low hydrophobicity, small water drop penetration times, both before and after the fire. But under the shrubs, even pre-fire, meaning in some cases it hadn't burned for about 40 years, you have really high hydrophobicity. And then after the fire, in some places, it gets even higher, which makes sense at sites like this one on the right, where you can see we burned and there hadn't been a fire for 41 years. The big sagebrush completely incinerated. You can see that's affecting the soils a lot more than the plot on the left, that it had only been 5 years since fire. And those grasses didn't even burn no matter what we did to them with a torch. And it's hard to get information about these long-term interacting effects between different fires because the field studies we have on fire's impact on hydrology mostly only cover about 5 years of time at most. Many of them are only 1 year or less after a fire. And also a lot of the studies we have are concentrated in the Western US, smattering in Europe. So there are a lot of geographic and temporal and fire type situations that just are not being studied as much as others, which sort of limits our information and ability to predict what's going to happen in new areas. So some take-home messages. Fires can lead to either wetter or drier soils, depending on your conditions, the fire behavior, where you are. There are some really complex feedback loops that you need to keep in mind that also make it really hard to predict what the interactions are going to be between soil moisture, fire behavior, and vegetation. And it's hard to quantify some of the connections in these feedbacks because most of our existing literature only covers relatively high severity fires in the Western US for less than 5 years after the fire. If you are interested in any of the data I've shown here from Yosemite, most of it's available on hydroshare.org. You can just search for my name and it will show all the data that I've posted. If there's something you don't see, feel free to email me. And before I stop, I just want to thank all the sponsors of this work, including NSF, ERDIC, Army Corps, USGS, the Park Service, and the many, many people who hiked all over Lillooet, other areas. Also, Joshua, who's in the room, has a great poster outside on the sagebrush work. And also, if you're interested about the literature search where I showed the map and the summary of data, you can find all that literature at ufdp.dri.edu. Have literature and data sets related to post-fire hydrology, including soil moisture.
All right, do we have any questions?
And we did have a request from online to please repeat the question before you answer.
Mhm.
I'm gonna trade places so you
Okay.
can answer and then I'll get slides up.
Please pull it up. Questions in the room? Not seeing any. I got a question.
All right.
So you mentioned that the research being done on wildfire, our soil moisture impacts on hydrology after wildfires was spatially and temporally limited. Is that because the proposals aren't
Mhm.
expanding? Like, how would you solve that problem? What's your recommendation? Kind of chip away at that.
Yeah, I mean, I think partly it's happening some of where, oh, sorry, repeat. Yeah, so the question is, what's, okay. Yeah, so the solution to not having good coverage, I mean, part of the solution is longer funding cycles, which I'm not sure how to solve that. That's for politicians or foundations. But yeah, it's really hard to, study what happens for 20 years after a fire, because how are you going to keep funding going for 20 years? But I think it's great that organizations like CAL FIRE are getting interested in the soil moisture question, that maybe partnerships like that can help to sustain some of these longer term observations. But yeah, I think just a lot of the funding is going to sort of just a handful of researchers who are interested in specific areas. And also places like California gets a lot of funding because there are a lot of people and resources there subject to fire. The Nevada funding we got through the EPSCoR program, which is specifically aimed at increasing research funding available for states that don't traditionally get a lot of research funding. So programs like that are really helpful. But yeah, I think connecting practitioners with researchers hopefully can help make some of these things sustainable by having sort of a key audience who is interested and invested in keeping this kind of work going forward, and yeah, creating usable tools that are going to last.
Thank you. Mike, do we have any questions online?
And that'll be our last
Have you
one.
seen any changes in spring activity post fire?
Changes in spring, like water coming out of the ground, or? Yeah, I don't have any specific measurements that can show directly that there's been increased spring outflow, but there definitely seem to be places where we have increased infiltration. You have more snow melt reaching down into the deep groundwater. I have heard anecdotal evidence of, springs that had been dry for years that started discharging after a fire because there's less transpiration. Yeah, more water can go to the groundwater rather than going to roots. But I don't have, but it's part of what's really hard of studying hydrology in the Western US is that it's so variable year to year. It's really hard to attribute what happens in a given year to a fire. Like this fire happened in 2017, which was also one of the wettest years on record. So there were a lot of unusual things that happened hydrologically. We say, but is it because of the fire? Is it because of this gigantic snowpack that happened everywhere? So I would say I do expect that there are differences in springs, and that has been shown in some places, but it's hard to get direct evidence. And just in case they were talking about spring the season, the spring snowmelt is definitely affected by fire, which affects green up and type of vegetation coming in.
Thank you so much.